All right, I'm going to start a brand new chapter titled The Periodic Law. And so we are going to look more in depth with the periodic table and look at patterns and trends and how did scientists develop this beautiful way to organize all the elements. Okay, so here we go. First section is titled History of the Periodic Table. So I'm going to talk about Dmitri Mendeleev and Moseley and how they helped contribute to the development of the periodic table that we know today, describe the modern periodic table, discuss how it's useful, how it's been used to predict physical as well as chemical properties of elements, and then finally just talk a little bit about the, how it's arranged by increase in atomic number, right? And how does that relate to the periodic table? So a little bit of a brief summary of the history of the periodic table, because your book just kind of skims over, and I just want to talk a little bit about it here. So I'm going to start off around the 1800s here with a man named Jöns Jacob Berzelius, and what he did is he developed a table of the atomic weights, and not only that, he introduced letters to symbolize elements. And at the time when he was studying chemistry, the elements of the earth that were known, there were only 33 of them. And so here's just an idea of the late 1700s, how we used symbols for different elements. I really like mercury, because mercury's, really bad, toxic, right? Little horns up there. And in the early 1800s, how it's changed a little bit. But then Jöns Jacob Berzelius looking at adding letters to symbolize different elements. Johann Dobereiner, 1829, discovered triads. That's what I mean by triads. Chlorine, bromine, and iodine. That is a triad. All these elements had similar properties. They behaved in similar ways. Here's another triad. Calcium, 88 Ba, that would be barium, and then 137. That can't be strontium, is it? No. What is 137 here? 40. Oh, they're looking at atomic weights here. Yeah, 88. No, that's not. Yeah, strontium. So this is strontium, this is barium. So these numbers represent atomic weights. And then finally, lithium, sodium, and potassium. So there were 53 elements known when Johann started, examining the periodic table, but the law of triads. By 1860, more than 60 elements had been discovered, but there really wasn't a way to accurately determine the atomic mass or the number of atoms in a chemical compound. And not only that, different chemists use different atomic masses for their experiments. So you can see that we have a lot of confusion going on in the scientific community just because everyone's doing their own thing. This periodic table right here, okay, so I really like this diagram for a couple of reasons. One, the ones highlighted in red or orange are elements that were known at this time. Okay, so there's about 60. I think I counted, it was short too. But not only that, it takes the lanthanum and the actinide series and it sticks it in front of the transition metals. And then here's our P block, if you remember way back in chapter 3, 4. So there it is. There's that diagram I told you. Could you imagine a poster on my wall that's this long? Or maybe it wouldn't be quite long, but the numbers would be, or the letters would be a lot smaller. So you'd really have to squint to take a look at the periodic table that's in the front of my classroom. Okay, so by September of 1860, they were like, we gotta unify, we gotta get our act together, get a common language. So they held their first International Congress of Chemists back in Germany. So they settled the issue of atomic mass, determined the atomic mass of those elements known. So hey, this is the number we're going to use. Stanislao Canizario, totally butchered his name there, developed a method for measuring relative masses of atoms, and he helped agree on the standard values for those atomic mass. So thank you, Stanislao. So now we're starting to get a common thread going along here with with all the scientists, with all the chemists. John Newlands, 5 years later, came up with the law of octaves. So what he noticed was that there was a pattern every time after every eighth element. So hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, and then we have fluorine. And you notice that hydrogen and fluorine were very reactive. And if we look at those electrons, okay, those electron configurations, fluorine needs one more to satisfy its full octet, so it's highly reactive. And hydrogen has one valence electron, and it needs one more to fill its outer shell, so it's also highly reactive. Now you notice that we skip over neon, because neon is a noble gas, and I'm pretty sure at this time maybe neon wasn't discovered yet. But then we go sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Hey, fluorine and chlorine. Chlorine sits right underneath fluorine, and so you just notice that after every 8 it repeated, and it did this very nicely until we got to the transition metals. So he's like, hey, I wonder if it's true for all the elements here, right? Chlorine, potassium, calcium, chromium, titanium, manganese, iron, cobalt, nickel. Oh, crap, something's wrong here. So the law of octaves is pretty good for the front part of the periodic table, but then when you start to get into the transition metals, it doesn't, the pattern is lost. So in steps Dmitri Mendeleev, this man right here. So what he did is he grouped elements by their properties. So he took these elements and he wrote them on cards, and he listed their observed physical and chemical properties, and he just sat down and started to lay out these elements and arrange them by their properties. And he also was looking for patterns, and he noticed that when you arranged the elements in order of their increase in atomic mass, those chemical properties that he noted on those cards appeared at regular intervals, hence the word periodic. So that's why it's called periodic tables. Periodic table, I should say, not tables. So here's just some work, from his actual journal. You can see that I scribbled out some, rewrote, circled, hey, there's probably a triad going on there. But you started to see the patterns coming out. So Mendeleevs table back in 1869 looked something like this, okay? However, there were some problems with it. So you notice that I have here boxed the triads from the first slide, okay? Triad. Okay, the ones boxed in pink here contradicted atomic masses by their contradicted the atomic mass. So, he arranged them according to increase in atomic mass, and it's so far so good. But, nickel should be listed in front of cobalt. But then when he did that, nickel didn't fit in with the properties of RH, which is, what the heck are you, cobalt, rhodium, and then IR, I know, is iridium. So he, flipped these around. So there's some areas on the periodic table where, it's not 100% true. But Mendeleev did it by atomic mass. I don't remember what the stars are. You'll also notice that there are some gaps in the periodic table. And these are elements that are just not discovered yet. And so I have a short video here. I'm not going to show it because I know YouTube's going to cut it out. So I'm going to put the link in and you can watch it on your own. But it's a great summary of Mendeleev and how he developed this. So here's an example of some gaps. Okay. So you notice we have a couple gaps here. And this is just one example of the gaps. So he actually predicted elements to be discovered. He called it Eka aluminum. I don't remember if Eka means before or after. So let's see if he has aluminum on here. It must mean under or after. So here's aluminum, and this element right underneath aluminum, he actually predicted. So take a look at calcium. The atomic weight is 40.1. Here's titanium, 47.9. So just based on his properties, he said, oh, you know what, this element has to be between 40.1 and 47.9. Okay, so he could predict properties of it. And other properties he had on his card: density of metals. So these were the predicted properties. Okay. And then when it was actually discovered, 10, 15 years later, they named it gallium. And if you look at the observed properties, hey, you know what? It's really close to 6. Hey, the melting point is really low, 30 degrees Celsius. Wow. Think about the human body temperature, 37 degrees Celsius. Here's the oxide formula. Here's another one, boron. Where are you, boron? Boron, after boron. So we've got this gap here. Okay, he made some predictions. Hey, the density is going to be 3.5, but you know what? The actual is 3.87. So a little off there. Solubility of the oxide dissolves in acid. You know what? It dissolves in acid, and so on and so forth. So, cool. Some questions that remained from Mendeleevs table. Number 1, why could most of the elements be arranged in the order of increase in atomic mass, but a few could not? Why do we have these discrepancies here? Second, what was the reason for the chemical periodicity that we saw? Why does it repeat? So in comes Henry Moseley, early 1900s, and he noticed a pattern that fits better than the increase in atomic mass, and that was the number of protons that it possessed. So this answered the first question. Why can most of the elements be arranged in the order of increase in atomic mass, but a few cannot? Well, instead of doing it by mass, do it by the number of protons. So if I take a look at iron has 26 protons, cobalt has 27, and nickel has 28. Hey, that's way better than mass. Now we don't have that discrepancy if we just base the periodic table solely on mass. So this is called the periodic law. Physical and chemical properties of the elements are periodic functions of their atomic numbers. So it's based on the number of protons that an element possesses. Okay, I'm just going to skip that diagram there. Okay, so answering the second question, what was the reason for this repeat of chemical properties? It has everything to do with the number of electrons in its outermost energy shell. Okay, so elements in group 1 are highly reactive. Okay, because they want, they need 7 more, but they're just going to give up that 1. Elements in group 18, they're the noble gases. So their electrons in the outermost energy shell, that it's completely filled. So they are inert. They are unreactive. So just to recap here, Daubigner, 1829, Triads. Newlands, 1865, the rule of octaves. Mendeleev arranged it by the atomic mass, repetition every 8 or 18. 8 or 18. Predicted 3 elements not yet discovered. Henry Moseley, early 1900s. Elements are arranged by increase in atomic number, not mass. Now, the modern periodic table is arranged by both atomic number and its properties. So the discovery of the noble gases, Lord Rayleigh and Sir William Ramsay discovered quite a few. 1894, argon, the lazy one, discovered when he was trying to isolate nitrogen. 1895, helium, found on Earth in uranium minerals. It's also found in the sun. They discovered that back in 1868. 1898, neon, the new one. Krypton means the hidden one. Xenon means the alien one. Radon was 1910. That's not Lord Rayleigh and Sir William Ramsay. As a result, we created a new group in between 17 and 18, and that is group 18. 17 and 1, sorry, and that is group 18, called the noble gases. There are 14 elements that make up the lanthanides, 58 through 71. And the actinides make up another 14, 90 through 107. So Glenn Seaborg discovered 7 elements beyond uranium. Okay, and as a result, the actinide series was developed. Fun fact, Seaborgium is the only element publicly named after a living person. And I was just going to look up the number on that one, but I'm not seeing it on my periodic table, so I'll have to look it up later. the newest elements, in case for those if you're really, really curious. Yeah, we've discovered quite a few. My periodic table is not up to date. And in fact, a lot of these still don't have names. But you can see here, when you combine zinc 70 with bismuth 209, you create element 113. Here's element 115, 117, 118. So basically you're just taking two atoms and smashing them together. Okay, so that does it for the history of the periodic table.